Dear students, this is the problem statement. What we have to do today, we are going to design a rigid flange coupling. Input shaft transmits power and RPM is given. Service factor is also given. We have to select suitable material and design coupling. This is about the problem statements. Why? It's an open-end problem. Open-end means, first of all, we have to select the material, then their properties, then FOS, then find out the permissible stresses, and then we will proceed. But in examination or university examination, you will find all the data may be available to you. You can refer that data and accordingly solve this. Now I will start. Now from this given problem statement, first of all, what are the things given that you have to note down? That is about the given data. The first of all, you can write down here given data. After reading problem statement carefully, the first thing is always the read problem statement carefully in design of machine engineering, and after that you can write down the given data. So what is given? Power is given 37.5 kilowatt. Then again, shaft rotates at which RPM? Here RPM is given 180 RPM. Then service factor is given 1.5. So what you have to do? You have to use the design torque. So after power and RPM, you will get the torque. You know the relation, power is equal to 2 pi n mt upon 60. By using this expression, what you will get? Mt, that is torque transmitted. And this is torque rated torque. This torque multiplied by 1.5, you will get the design torque. And we are going to use this design torque or tau maximum in our design of the different parts. Try to understand. And why rated torque? If the electric motor which is connected to some machine, so initially you know very well the position that the rotor which is stationary position during starting initially torque required which is more, and during running condition is less. So to take the care of that initial requirement of the torque, it is multiplied or service factor which is used here. Try to understand. That's why design torque by multiplying service factor to the torque which is calculated from the power and RPM. Try to understand. Always again here while designing the the couplings or other things which are related to prime movers, also if electric motor is there, always you have to consider some service factor, and based on that you can do this design torque. Try to understand, or instead of design torque you can say maximum torque which is required to design the other elements or the component. This is one thing. So therefore design torque is equal to 1.5 times the rated torque. So we will calculate rated torque from the power and RPM. I will explain that later on while designing the shaft. Then selection of material. I have already explained in design of shaft during the discussion of design of shaft. That is plain carbon steel 30C8, 35, 40C8, 55 or alloy steels are the material generally used for the shafts. Now here you can select suitable material. You can refer the data book, or even though in many books it's available. Generally plain carbon steel grade 40C8, 50C8 are used. So here we can select 40C8. So for 40C8 in data book you will get SYT is equal to 30 Newton per mm square. Again SUT is also given, but shaft is going to subject to torsional, the twisting or torsional shear stresses are going to induce in it. That's why I have taken only SYT. Otherwise you can write SUT, no problem. Second thing, factor of safety. Generally I have already last time also told the maximum it is in the range of 2 to up to 3 you can take, no problem, but FOS should be in between. I have taken that it's 2.5. Then for keys and bolts, another elements are key bolts. Now here in this design of rigid flange coupling we have selected plain carbon steel grade, that is 30C8, SYT 400 Newton per mm square, FOS 2.5 here. So you have a choice. You can take FOS in this case 2.25 also, no problem. But it's totally you have to refer the data book, and based on the application and you can select the value of FOS in data book. All things are given. Again for plain carbon steel 30C8 SYT 400 Newton per mm square is given. Then again here you will find keys. We are going to the keys, two keys, that means for input shaft, output shaft. Again, how to design the key? Design of key based on against, the shear failure against crushing failure. For a crushing failure, what we have to do? We have to find out the shear stress induced in the key as well as the crushing stress induced in the key. Crushing stress is nothing but a compressive stress. Therefore, we have to assume here the relation between compressive and tensile stress. Now, for that purpose, here we have assumed compressive yield strength is 150% of the tensile yield strength. And I have already told always compressive strength is more than the tensile yield strength. And maybe what you can assume here 200 times also, no problem. But here in this case, it is assumed 150 times than the tensile yield strength. Try to understand. The next one, flanges. Now another component, input flange, output flange, and generally flange which is manufactured by casting process. Gray cast iron is the material which is preferred, and FG 200 is the nomenclature or designation which is used for the gray cast iron. But sometimes in examination directly it may be mentioned like this: flange which is made up of gray cast iron FG 200. FG 200 means gray cast iron, 200 means SUT. Try to understand. So they are not giving you SCT further 200 Newton per mm square. Once they are written FG 200, that means you can assume it's a ultimate tensile strength for gray cast iron. The SUT 200 Newton per mm square. Again here, for the cast iron, FOS is always more. I have already told you can take the 4, 5, 6, no problem. So in this case, we have chosen as a 6. Second thing here in cast iron, now here a hub which is made up of gray cast iron, flange which is made up of gray cast iron. While designing the flange, again hub and flange, you will find hub is going to subject torsional shear stresses. Flange is also going to add the region of hub and the flange. You will find that is because of the torque transmission, again torsional shear stress, and that's why here for the gray cast iron, ultimate it's a brittle material. Ultimate tensile strength is given, but what we have to do? We have to find out ultimate shear strength to design hub or to find out the torsional shear stresses in the hub and the flange, and that's why what we have to do, we have to find out ultimate shear strength. And generally ultimate shear strength is 1/2 of the ultimate tensile strength. Try to understand, ultimate shear strength is 1/2 of the ultimate tensile strength. And here compressive strength generally 2 times or 200% I am talking, that means 2 times the tensile yield strength. Try to understand. That's why I have written here ultimate tensile strength is 1/2 of the ultimate tensile strength. This is about the material selection, their properties, and the FOS. And once you know the SYT, SUT, FOS, then relation between tensile strength and compressive yield strength. So what is the next step? Find out permissible shear stresses. Now let us see in another here. The next step is find out permissible stresses. Now consider first element, that is shaft. Now for a shaft, which material we have selected? Plain carbon steel for TC at SYT 300 Newton per mm square, FOS 2.5. Now shaft is going to subject to torsional shear stress that we have to find out. So what we have to do? We are going to find out torsional, that is tau permissible. Now tau permissible we know very well because we have solved number of problems in design of shafts also, in case of key also, and in case of design of simple elements also. Now here tau is equal to SSY upon FOS. We know very well. Again SSY means 0.5 SYT, SYT 380. You can substitute here. What do you get? Tau permissible for the shaft 0.5, SYT means 380, FOS 2.5. What you will get here? Tau permissible for the shaft is equal to 76 Newton per mm square. This is 1. Then similarly, we can find out permissible stresses for key, bolt, and cast iron or flanges. Now let us see. Key and bolts are made up of same material, that is 30C8 or plain carbon steel 30C8. Now here SYT is equal to 400 Newton per mm square, FOS 2.5. So what we have to do? So first of all find out, because key is going to fail against here, bolts are also going to fail against here, as well as crushing key is also going to fail against crushing. So what we have to do? First of all find out tau permissible for key, tau permissible for bolt. They are made up of same material. The same value will get the tau permissible for bolt and key is equal to SSY upon FOS. Again 0.5 SYT upon FOS. But in this case SYT how much? 400. That's why 0.5 into 400 by 2.5. So you will get here tau permissible, this value, tau permissible for key and tau permissible for bolt. How much value? 80 Newton per mm square. Try to understand. Then again here we are going to design a key against crushing failure. We are going to design a bolt against crushing failure. So what we have to do? We have to find out the compressive permissible stress or crushing stress. How to find out it? The sigma C is equal to SYC upon factor of safety. But what we have done while selecting the material, we have assumed here. I have written. Look at this. In this case here, we have already assumed the compressive strength is 150% of the tensile strength, and that's why here you will find this SYC is equal to 150 means 1.5 of SYT. Look at this. 150% means 1.5 times SYT upon FOS. And if it is sometimes you can take 2 times SYT upon FOS, no problem. Try to understand. But in this problem we have assumed 1.5. That's why 150 times 1.5 SYT upon FOS. SYT for key material that is 400, you can substitute for bolt material also, and you will get 240 Newton per mm square. That means this is permissible crushing stress for key and permissible crushing stress for bolt is equal to 240 Newton per mm square. And this is permissible shear stress for key, permissible shear stress for bolt, that is 80 Newton per mm square. Try to understand. That means for shaft, for key and bolts, we have calculated here permissible stresses, maybe permissible shear stress, permissible crushing stress. Now third component is flange. Now let us find out permissible stress for flange. Now here flange which is made up of grey cast iron, Fg is equal to 200. The SUT is equal to 200 Newton per mm square, and FOS we have selected 6. But here in this case, you know flange. Flange hub is made up of cast iron and flange part is made up of cast iron. And yesterday we have discussed how while designing the hub is a hollow cylindrical part or a sleeve. It is going to subject a torsional shear stress. And similarly at the hub, the flange is also going to subject the torsional shear stress. That's why what we have to do, we have to find out the torsional shear stress means tau permissible for this flange. But how to find out? For that purpose, we have assumed here ultimate shear strength is 1/2 of the ultimate tensile strength. Try to understand. Now here all these are the the assumptions. For different materials you will get it is in the range of half or 0.45 or 0.4 SUT, 0.45 SUT, like this. So in general you can assume here 0.5 or half of that, and that's why tau is equal to SSU, that is ultimate shear strength upon FOS. But ultimate shear strength we have assumed half of the SUT, that is 0.5 SUT upon FOS. The 0.5 SUT means how much? Fg 200 means SUT, that is 200 by FOS, you will get 16.67. This is tau permissible for what? Flange. Flange means hub is made up of the grey cast iron and flange is made up of the grey cast iron. Try to understand. And this tau we are going to use for a hub design as well as the flange design. This is about the permissible stresses. This is step number 2 after selection of material. So what you have to do? Find out the permissible stresses. Now here, now let us start design of coupling. Now again here yesterday we know very well while designing the coupling. Now here in this statement it is not mentioned whether it's a rigid coupling or protective coupling. We always go for a protective, it's a safer one. That's why we are going to design a protective, and only what in the difference between unprotective and protective, only you have to find out the thickness of the protective part, nothing more than that. Only one parameter that you have to add it here. That's why always design, if it is not mentioned, design for protective type flange coupling. Now then deciding protective type flange coupling in your mind, again this is the construction, and after calculating all the dimension you have to construct it as per the problem statement. You know very well This is the protective type flange coupling. This is diameter of the shaft. Then capital D is the hub diameter is equal to 2D. Then PCD, P circle diameter of the bolts, that is capital D1 is equal to 3D. And outer diameter of the bolt, you can take D2 is equal to 4D or 4D plus 2T1. 2T1 means thickness of that projected part. TP means protective part thickness, flange thickness, and TF means thickness of the flange, this thickness, right? And D1 is the nominal diameter of the bolts, right? And length, L is the length of the hub is equal to 1.5 times the diameter. This is about the construction of a plane. So what we have to do, already yesterday we have discussed, while designing the rigid flange coupling, the first of all find out diameter of the shaft. Now let us proceed to this activity. Now here, again I have written here some standard empirical relations we are going to use in our design. And from the construction also, you know very well, outer diameter of the hub, D capital D is equal to 2D. You can write down, no problem. The circle diameter of the bolt, that is D1 is equal to 3D. Outside diameter of the flange, D2 is equal to 4D, 4D or 4D plus 2 times T1. Or length of the hub is equal to 1.5 times D. Thickness of the flange is equal to 0.5 times D. Thickness of the protective circumferential flange, that is 0.25 times the D, where D is the sub diameter. So first of all, let us find out in design. First step is design of shaft and find out shaft diameter, that is small d. How to find out? Again, you know very well, to transmit the torque. Because of that, torsional shear stresses are going to induce in the shaft. And we know very well in second year also, you already studied in first unit also, design of simple machine element. We know very well how to find out the torque transmitted by the shaft. And we know simple expression, tau is equal to mtr by j. J is the polar moment of inertia. For circular shaft, pi by 32 into d raised to 4. Mt is torque transmitted. R means d by 2 diameter of the shaft by 2. Distance to the outermost fiber from the neutral axis. And from this expression, you will get this equation. Tau is equal to 16 upon pi d cube. Now here, what you have to do, you have to substitute tau permissible for the shaft. We have calculated this value. What is the tau permissible for the shaft? Look at this here first. 76 Newton per mm square. Here, MT means torque transmitted. That we have to find out from power and RPM. And from substitute this torque, substitute this tau permissible and find out the. Now let us see how to find out. For that purpose here, click up. Now here, you can use the expression power is equal to 2 pi n mt upon 60. Now here power is given in kilowatt. That's why multiplied by the 60 into 10 raised to 6. You can arrange the equation. You will get mt is equal to 60 into 10 raised to 6 into kilowatt means power. Try to understand. Upon 2 pi n and into service factor 1.5. Here you can multiply. That means directly you will get here design torque. Or otherwise, first of all, what you can do, you can use this expression, find out mt and then multiplied by service factor 1.5, you will get this value, no problem. This is service factor. The power, what you have to do from power and RPM, you can find out the MT. Power is given kilowatt, that's why multiplied by 10 raised to 6, 37.5 into 10 raised to 6 into service factor. Directly here it is multiplied, means here you will get which torque? Design torque. So here you from this by using power is equal to 2 pi n mt upon 60, you will get torque. Again multiply that torque by 1.5, you will get design torque. This is design torque. Try to understand. Then next, once you know the design torque, I have already explained you, on earlier slide this expression. So we are going to use this expression, tau is equal to 16 mt upon pi d cube. So by using this expression, what we have to do? Tau permissible, we have already calculated 76 mt. You know very well, we have calculated it from the power. Then what you will get? D cube, that you have to find out, or D. So by putting or substituting the values of mt, substituting the values of tau permissible, you will get the value of D. D means shaft diameter, that is 58.48. Standard one is we are 60 mm. Try to understand. That means from power and RPM, we have calculated torque. Torque is multiplied by service factor, you will get design torque. By using this design torque, we have calculated, substituting the value of tau permissible for the shaft, we have calculated shaft diameter. Try to understand. Now here this value is 58.48. that is 60 mm. Now, once you know the diameter, what you have to do by using empirical relation, we can easily find out what other dimensions of the coupling. Now, let us find out it. Outer diameter of the hub, that is 2D, 120, 60 multiplied by 2, 120. With circle diameter of the bolt D1, 3D, 180 mm. Then outer diameter of the flange, 4D. If you are going to use the 4D, you will get 240, and another expression 4D plus 2 times T1, that is 270 mm. Try to understand. How here? Because in figure I have already mentioned here. Look at this. Don't make confusion. You can take D2 is equal to 4D or D2 is equal to 40 plus 2T1. T1 means 0.25 T. You can substitute here, so you will get 4D. So you have a choice. You can D2 is equal to 4D or D2 is equal to 4D plus 2T1. Both equations. Uh, that's why I have written both here. The outer diameter of the flange 4D to 40 and another expression 270 mm. Then length of the hub L is equal to 1.5 times D is equal to 90 mm. The thickness of the flange TF 0.5 times diameter 30 mm. Thickness of the protective part 0.25 times D, that is 15 mm. And DR means races diameter here 1.5 times D, that is 90 mm. You know DR. Look at this here. Once again, yesterday I already explained here. This is for the projection and races provided on the flanges to have a precise element, that is DR is equal to 1.5 times D. That means by using empirical relation, we will get all the dimension. Once you will get all the dimension, what we have to do, whether this coupling is going to sustain by using this dimension, that we are going to check by determining the stresses induced in different parts. If these induced stresses are less than the permissible stresses, then we are going to say our design is safe. Otherwise, what you have to do, you can increase the shaft diameter and once again check it. If even though it is going to fail, you can change the material. These are the the different approaches that you have to follow while designing the any mechanical system or component. Try to understand. Now let us see. Once you have a shaft diameter, you can find out all the dimensions of the coupling. Now let us next proceed. Next step, design of hub. Again, I have already explained also. In design of hub means this is input shaft here. This is the flange part and hub. We have considered here. I would like to show today also. No problem. Look at this here. This part is the hub part here. Hub is a sleeve or a hollow cylindrical. It is a part of a flange, but while designing it, we have to take the care. It's a hollow cylindrical part or a sleeve, and it is going to subject torsional shear stresses. And I have already explained this. MUP is also a hub in this MUP coupling. Now it's a hollow one. And again, what is going to happen as the shaft rotates because of the key, hub is also going to rotate. Because of that, torsional shear stresses are going to induce in it. So what we have to do in design of hub, we know that is capital D is the hub diameter is equal to 2 times the shaft diameter. Already we have calculated. So what we have to do, it's a hollow cylindrical part. That's why we have to use the expression of a hollow shaft. So for a hollow shaft, we know variable MT is equal to pi tau upon 16D raised to 4 minus small d raised to 4 by D. Again, you know very well in some of the cases you will find one factor which is introduced, that is the small k is equal to small d by capital D ratio of inner diameter to outer diameter also. It's okay. The D is the outer diameter, hub means 2 times the shaft diameter. And the small d is the inner diameter means shaft diameter. You can substitute D is equal to 2D. D means shaft diameter, that is 60, here 120, here 120, and MT means torque transmitted design torque. You can substitute all these values. And what you have to do, you have to find out this tau. Try to understand. That means torsional shear stress induced hub that we are going to calculate by using this expression. Now here I am going to find out this. J means polar moment of inertia, that is pi by 32. You know, here in this case d raised to 4 minus d raised to 4 by d. Now here, so what you have to do, you can use this expression for a hollow shaft or a hub. Hub is a hollow cylindrical part. That's why directly you can use this expression. Substitute capital D is equal to 120, small d is equal to 60, capital D 120. Then MT means design torque, and find out this tau. So what you will get here, this tau is equal to 9.38 Newton per mm square. This torsional shear stress induced in the hub is this, but hub which is made up of which material? It's a part of a flange. That means gray cast iron. And for gray cast iron, permissible tau, we have calculated in first step, that is 16.67. I will show once again here to you. Look at this. How much is the permissible shear stress for this hub and the plane? That is 16.67. Now here in calculation, you will find this induced torsional shear stress 9.38 is less than 16. You can see your design is safe for the hub. So in the hub case only, what you have to do, find out torsional shear stress by using this expression, considering it as a hollow cylinder or a sleeve, try to understand, or a hollow shaft. That's all. This is about the design of hub. Now let us see design of key. Again, you know very well how to design the key. So for that purpose here, you have to assume the key. You can assume square key, flat key, rectangular key. And generally the rectangular key or flat keys are preferred. So now here I have shown here the construction of the key. B is the width of key, H is height of key, L is length of key, that is 1.5 times. The assume rectangular key, the width of rectangular key D by 4, and height of, always try to understand, width of the key is greater than height of the key. Therefore, H is equal to 2/3 of the width. And 2/3 of width means d by 4. You can substitute here, you will get H is equal to d by 6. So from width also you will get H, or directly you can use d by 6, no problem. Once you will get a T means shaft diameter, 60 by 4, you will get B is equal to 15. I have written here, look at this. And H is equal to 60 by 6 means you will get 10 mm, and length of the key, that is 1.5 times d, that is 90 mm. So you have to find out all these dimensions, but whether these dimensions are suitable for this application to transmit that 13 point something kilowatt power, that we have to check it. How to check it? Because key, we are going to key again, key is going to fail against shear and against crushing. That's why what we have to do, we have to find out the shear stress induced in the key, we have to find out the crushing stress induced in the key. Now let us find out shear stress induced in the key. And we know very well shear stress induced in the key, which is given by 2mt upon dBl. Mt means the torque transmitted, D is the shaft diameter, B is the width of the key, L is length of key. So what you have to do, you can substitute all this value, find out this key, tau. Now induce shear stress in the key. You can write here, design against shear failure, 2mt upon dBl. Substitute all this value, you will get tau. Tau induce, shear stress induce 58 Newton per mm square. But here for a key material, permissible shear stress is 80. The induced stress is less than 80 Newton per mm square. You can see your design is safe. Similarly, what you have to do? Design of key against crushing failure. For crushing failure, sigma C is equal to 4mt upon DHL. And we know MT, design torque, you can substitute. D shaft diameter 60, H here you will get 10 mm, L length of the key 1.5 times the diameter. You can substitute all this value, you will get sigma C in the range of 198 or 199, no problem. Sigma C is equal to 98 Newton per mm square, and this is again less than the 240 Newton per. This is about the crushing failure. This is the permissible crushing stress for key. Once again, I would like to show here, in permissible stresses we have calculated. Look at this, for the key, sigma C permissible 240, permissible crushing stress 240. That's why you have to check again key as well as for the bolts also. Here you will find this is less than, sigma C is 198, less than 240. That means you can say, that means you can use B is equal to 15, H is equal to 10, length is equal to 90 mm, no problem. Right. This is about the design of key. The in design of key, what you have to do? By using this relation, find out a dimension, check it against by calculating, determining the induced stresses, shear stress and crushing. If these induced stresses are less than the permissible, you can see your design is safe. This is design of the key. Now let us design flange. Now again, yesterday we have already discussed during the session, flange. Here the hub, how the flange transmit the torque through the shaft, key, then hub, and here flange. Again, it transmits the torque. That means it is going to subject to the shear. Right to understand. Shear failure of the flange may occur at this junction of the hub and the flange. Look at the cursor at this point. That's why what we have to do again here. In this case, we have to find out the shear stress induced at the junction of hub and the flange. Now, how to find out? Yesterday, I have explained the shear failure that we have to check. For that purpose, first of all, find out the shear area. The shear area here, this area we have to consider. The diameter is capital D. Then thickness of the flange is TF, and in circumferentially, that's why pi. The area under the shear is pi D into TF. The shear for means this shear area into shear stress. But here what is happening? Resisting torque. When it is going to transmit that torque, resisting torque is equal to shear force into d by 2. That is half diameter by 2. So by using this expression, you can find out this tau. So you can use mt is equal to pi into d into tf, that is shear area, into shear stress into d by 2. D is the half diameter, that is 120. Then TF, thickness of the flange, that is 0.5 times the diameter of the shaft. Then capital D, hub diameter. MT, design torque. You can substitute all the values and find out this tau. That is shear stress induced at the junction of the hub. So here you are, after substituting MT, capital D, TF 0.5 times the diameter, D is half diameter. So what you have to do? You have to calculate this tau. Here you will get this tau is equal to 4.40. And this calculated 4.40 is less than the 16.67. Again, flange is made up of grey cast iron, and permissible stress for this grey cast, that is flange and the hub, we have already calculated 16.67. The calculated value 4.40 is less than the 16.67. You can say your design is safe for the flange also. This is about the design of flange. Now here in this case, only one part is remaining, that is design of bolt. Now let us see how to design the bolt. Now here in design of bolt, yesterday I have told you, so before designing the bolt, again bolt, two flanges are mounted on it, so because of that shear failure of the bolt. And again, two cases that we have to consider. If there is no clearance, tightly fitted, and bolts are fitted in rimmed and ground hole, that means there is no relative motion. That means bolt is going to fail because of this crushing stresses also. That's why while designing the bolt, you have to use two criteria: shear failure as well as the crushing failure, and another analysis based on the large clearance hole. That is your choice, that you have to assume. But generally, to have a proper fitting of the flanges by using nut and bolts, so assume no clearance and bolts are fitted in rimmed and ground holes. So we have to assume this case. That means we have to design the bolts against shear as well as the crushing failure. This is one thing. Second thing, again here shaft diameter calculated is 60 mm. So what you have to do? We have to decide the number of bolts. Now look at this. Yesterday I have already told, if shaft diameter is less than or equal to 40, number of bolts are is equal to 3. If it is in between 40 to 100 or 80, that is 4. Then 100 and 186. Now here our shaft diameter is 60. That is, it is in between 40 to 80 or 100. That's why you can assume here n is equal to 4. So assuming n is equal to 4, let us design the bolt. Now look at this again. Yesterday I have already told. So we have assumed now n is equal to 4. But bolts, we are going to design two criteria: shear failure of the bolt. While when the flange or the bolt transmit this torque, the resisting force which gets induced, which is perpendicular to the axis of the bolt, given by the P. And how to find out this resisting torque? Mt is equal to this resisting force into this capital D1 means P circle diameter of the bolt by 2 into n means number of bolts. Number of bolts we have taken now 4. Why 4? Because shaft diameter is 60. Then we are going to, from this expression, you will get the resisting force, that is P, force acting on is bolt. Then shear failure of the bolt, tau is equal to simple expression, force upon area. What is the area of the bolt? Pi by 4 into d1 square. D1 is the nominal diameter of the bolt. So if what we have to do from this expression, you can substitute the value of P here by using this expression here. After substituting this value of P, that is mt here, so you can say 2 towards this side, 2mt upon d1 into n. You can substitute here. So what you will get, tau is equal to 8mt upon pi d1 into n into d1 square. The shear failure or shear stress. Now here what we have to do? We have to find out the nominal diameter of the bolt, that is d1. The bolts which are made of, bolts and keys are made up of same material, that is 30 C8. What you have to do? Use tau permissible for bolt material here. Mt is the torque. D1 is the PCD of the or P circle diameter of the bolt is equal to 3 times shaft diameter 180. N number of bolts, that is 4. And what we have to do? We have to find out this small d1, that is PC, nominal diameter of the bolt. And once you will get this, what you have to do? Find out the crushing stress induced in the bolt, that is P upon projected area, that is thickness of the flange into diameter, that is nominal diameter of the bolt. Now let us see in next slide how the calculations are carried out. And that's why I am going to use the equation. Diameter, it is in the range of 40 to 100, number of bolts 4. And we can use this expression, tau is equal to 8 mt upon pi d1 n d1 square. The tau permissible is given for the bolt material and key material, that is that we have already calculated from FOS 2.5. Tau permissible 80 Newton per mm square. You can substitute here. So what you will get? Mt, we know very well, d1 3 times the shaft diameter, n number of bolts. This is tau permissible. You can substitute. What we have to do? Find out d1. So you will get d1 11.49 or 12 mm. And once you will get the 12 mm, next step, what you have to do? You have to check for the bolt again crushing failure. And the crushing stress is equal to force upon projected area. Now bolts which are inserted, projected area means thickness of the flange into diameter of the bolt. Which diameter? Nominal diameter. D1, that is 12. You can substitute. Thickness of the flange we know very well, 0.5 times the diameter. P already calculated here. From this expression you will get the P, you can, or with this P you can substitute, no problem. After substituting this P you will get sigma C. The crushing stress induced in the bolt, that is 23 Newton per mm square, but it's less than the crushing stress for the bolt, that is 240. The 23 is less than 240. You can say your design is safe. In this way you have to design rigid protective type or unprotective type flange coupling. Try to understand. Once you will get all these dimensions, what you have to do, you can construct the diagram, a final solution. And what you have to do, you can construct the sectional front view, side view, or top view. It's a cylindrical one, symmetric one. That's why I construct any two view, that is sectional front view and side view. And you can substitute. TF means that is 0.5 times the diameter, TP 0.25 times the diameter, T1 0.2 times the diameter. All by using all the diameter of the shaft, 60 dr is equal to 1.5 length of hub, and construct this diagram properly. This is about the design of flange coupling. I hope you understand it very systematic way. Yesterday we have discussed and today we have seen one of the problem, how to design the coupling. This is about the today's session. If you have any query, you can contact us through the WhatsApp or a mail.